Hi, my name is Maria Gelepi and I am postdoctoral researcher at Aristotle University of Thessaloniki. In this session, I will present a work entitled Forecasting Day-Ahead Electric Load Demand on Greek Energy Market. This work was conducted in cooperation with Professor Anastasios Stefas in the context of Malena project. Malena aims to develop effective models for the accurate prediction of the energy load demand, energy production by the renewable energy sources, as well as personalized energy consumption management by individuals. The presentation is structured as follows. First, an introduction to the electric load demand forecasting problem, and the contributions of this work are provided. Next, the input features investigated for the electric load demand task are presented, followed by the proposed regularization method for improving the forecasting performance. Finally, the experimental evaluation is provided and some conclusions are drawn. Electric load demand forecasting describes the task of forecasting the aggregated expected electricity demand. Load demand forecasting constitutes a vital task since the inception of the electric power industry. It is accompanied by many applications, such as power systems operations and planning or energy trading. Therefore, it is of critical importance to develop models that allow for accurate load demand forecasting. During the recent years, deep learning provided powerful models for addressing various problems, ranging from image classification and retrieval to generic forecasting tasks. Besides, several deep learning methods have been proposed for addressing the load demand forecasting problem. For example, the paper called Deep Neural Networks for Energy Load Forecasting investigates the effectiveness of using convolutional neural networks for performing energy load forecasting. Next, the paper called Short-Term Load Forecasting with Deep Residual Networks introduces residual networks for the task, accomplishing remarkable performance. Finally, in the recent literature, there are also works that focus on Greek energy market. For example, the paper called A Novel Fuzzy-Based Ensemble Model for Load Forecasting using Hybrid Deep Neural Networks proposes a fuzzy RPF-CNN model for the task considering the Greek energy market. In this work, we also deal with the electric load demand forecasting on Greek energy market. We first aim to provide an evaluation study for selecting the optimal input features for training a day-ahead load forecasting model, as well as an effective model architecture. Our second goal is to propose a regularization method aiming to improve the baseline forecasting performance. So, regarding the input features, we investigate several inputs which are generally used in the relevant literature, such as previous load data and weather information. Real weather information of the day whose load demand we want to predict, that is the so-called target day, is not available. However, the vast majority of the works use the weather information of the target day, and so it is also used in this work. It should be noted that this assumption is generally made since temperature can be provided by the solution of another task known as air temperature forecasting. So, in the next table, the description of the used input features is provided. We use load data of the day before the target day, load data of the day 1 week before the target day and 1 month before the target day. Furthermore, the corresponding temperatures are explored as well as the temperature of the target day. Finally, two indicators of the target day being weekend or holiday are used. We expect that these inputs will help the model capture both short and long-term trends in the time series, while the last binary indicators will help the model capture unordinary temporal attributes. Next, regarding the proposed regularization method, the second target of this work is to improve the performance of the best baseline forecasting model. To this end, we propose a regularization method based on multitask learning. Multitask learning constitutes, in general, a way of improving the performance of a model which has been successfully applied on generic classification problems. Thus, apart from the basic laws used for forecasting, that is, mean absolute percentage error, we attach an additional regularization laws in the penultimate layer of the model. The additional laws enforces the model to maintain the similarities of the representations in the feature space generated by the aforementioned layer. Specifically, as depicted in the equation, each representation y in the penultimate layer is forced to come closer to the mean vector S of its n most similar representations in terms of a similarity measure. MAPE loss is used to realize the regularization. Therefore, the total loss for the regularized training is depicted in equation 2. The parameter lambda controls the balance between the forecasting loss and the regularization loss. So, moving on to the experimental evaluation. First, regarding the evaluation metrics, mean absolute percentage error is used as an evaluation metric since it is the most common evaluation metric considering forecasting tasks. Each experiment is conducted 5 times and the mean value and standard deviation are reported. Regarding the utilized dataset, we use load data provided by the Greek Public Power Corporation. We also use weather information derived from the open weather. For the model's training, we used 6 years of data, and for testing, 2 years of data. Regarding the implementation details, Adam Optimizer was used for training, where the initial learning rate is set to 10 to the minus third. The models are trained for 3,000 epochs. Batch size is set to 32 and the parameter lambda for controlling the balance between the basic and the regularization losses is initially set to 10 to the minus fourth and after 800 epochs is set to 10 to the minus third up to the end of the training. So, 3 sets of experiments are performed. First, we use a simple MLP model consisting of 4 layers and to investigate the input features for selecting the optimal ones for the day ahead forecasting task. Next, using the optimal features, we investigate the model architecture. Apart from the one initially used, we also use 2 MLP models with 5 and 6 layers respectively. Finally, using the optimal features and model, we perform experiments using the proposed regularization method, utilizing also different numbers of most similar representations. First, the experimental results for the input feature selection are provided in the table. 5 different cases are considered. Only load data of previous day, load data of previous day and previous week, and load data of previous day, previous week, and previous month. The fourth case also includes the corresponding temperatures and the temperature of the target day. And finally, the last case includes all the load and weather data and 2 binary indicators for weekend and holiday. As it is demonstrated, better performance is accomplished using all the considered features. That is, using all the features, the model achieves MAPE 2.110, while using only the load of previous day achieves 2.814. In the next figure, we also provide test MAPE throughout the training epochs for each of the 5 different cases. The same results are clearly illustrated. We can see, comparing the last 2 cases, that these 2 additional indicators can considerably improve the forecasting performance achieved with all the load and weather information, indicating that capturing weekends and holidays is of critical importance for the load demand prediction. In the next table, the experimental results considering the optimal model architecture are provided. As demonstrated in the table, apart from the initial MLP model, which consists of 2 intermediate layers and the input layer of 170 neurons and the output layer of 24 neurons for each of the 24 hours of the next day, we use 2 MLP models with 3 and 4 intermediate layers. The first MLP model consists of 79,000 parameters, the second one of 86,000 parameters, and the last and more heavyweight consists of roughly 200,000 parameters. Interestingly, the more simple and lightweight model is the optimal model achieving MAPE 2.11, while the heavyweight one achieves MAPE 2.31. The corresponding figure of test MAPE throughout the training epochs is provided in the next figure for each of the 3 MLP models with the same optimal input features. The superiority of the lightweight model is also illustrated. Finally, the experimental results for the regularized forecasting are provided in the last table. More specifically, the single MLP model with 2 intermediate layers and using as input all the features previously described serve as baseline. Then we apply the proposed regularization method on this model, considering the 2 and 4 most similar representations in terms of Euclidean distance for each representation. As it can be observed, the proposed regularizer improves the baseline forecasting performance for both the considered numbers of most similar representations. These results are also illustrated in the final figure. Marginally better performance in terms of MAPE achieves the proposed regularizer considering the 4 most similar representations. So, to sum up, in this work we dealt with the problem of electric load demand forecasting on Greek energy market. We first provided an evaluation study for selecting the optimal input features for training a day-ahead load forecasting model, as well as an effective model architecture. Then we proposed a regularization method for improving the baseline performance. The experimental evaluation indicated the optimal input features and model for the low-demand forecasting task, while the effectiveness of the proposed regularization method in improving the baseline forecasting performance was also validated. As I initially said, this work was conducted in the context of Malena project. Malena is funded by the European Union and Greek national funds under the goal Research, Create, Innovate. Thank you.